All right, gang, welcome back. Sorry, running just a little bit late today. Got off to a late start with a meeting, and it's kind of been cascading through the day. So let's get into this and get into it quickly. Today, we're going to talk about systems of equations. This is the first of several lectures we're going to have on systems. And you can kind of think of this as your gentle introduction to the universe of systems. We'll be focusing primarily today on 2x2 systems of linear equations. From there, we will eventually talk about 3x3 and larger. And we will learn how to handle general systems the smart way, which means matrices. But today we're going to cover section 10.1 on 2x2 systems of linear equations. And maybe introduce 10.2 on 3x3 and larger systems. If there is time. So far, I really have not had time with any of my other pre-calc classes to get through both of those. But 10.2 doesn't really have anything special that 10.1 doesn't. Just the systems are larger. There's only one place to begin here, and it's with a definition. A system of equations is a collection of equations, Now, it could have multiple variables in it, multiple equations, each one with multiple variables, meant to be solved simultaneously. Meaning you want to find the value of each of those variables that makes all the equations true at once. Such a system is called linear. If all the equations are linear. And what that means, say an equation with multiple variables is linear, just means that the variables only occur upstairs, never downstairs in a fraction, only ever occur to the power of 1, never squared or cubed, never under a square root, never in an exponent. We'll say all variables occur upstairs and only to the power of 1. Right, so these are linear systems. I'm going to show you some examples. We'll classify them by their size, aka dimension, and then we're going to talk about how to solve them. How about a couple more? Okay. So here are 4 systems. each of these are what we would call a 2x2 system. The first number there, when I like at the very start when I was writing 2x2 or 3x3, first number is the number of equations, so 2 equations. The second number is the number of variables. So each one of these has 2 equations and 2 variables. So we would call each of these a 2x2 system. What I want to do is just classify them as linear or nonlinear. So thinking about the definition above, is this first system a linear system or a nonlinear system?
Nonlinear?
Very good. This is a nonlinear 2x2 system. What makes this system nonlinear?
It's x squared, but it has to be to a power of 1.
Very good. This is what makes things nonlinear. In fact, this first equation, if you rewrite this, this is y equals x squared. That's a parabola, right? That's not a straight line. So it's another way to think about it, right? If the graph is not a straight line, then it's not a linear equation. Unfortunately, for higher dimensions, that doesn't hold, right? A 3-dimensional linear equation is not the same as his graph won't be a straight line. It will be like a plane or a hyperplane. But for 2x2s, we can think of it that way. Okay, so this first guy is nonlinear because of the x squared. What about the second guy?
It's linear?
Yeah, oh, wait, almost. So the first equation here, this one is linear, right? 2x minus 3y equals 1. That's a line with slope 2/3 and y-intercept -1. But what about the second equation? See anything that could cause us trouble in the second equation, violating this rule?
Square root of y?
Yeah, the square root of y, that's the same as y to the 1/2, right? So all the variables need to occur only to the power of 1. So this guy is also nonlinear. He is again a 2x2. And he's nonlinear because of this term. Right, square root of y is the same as y to the 1/2, which is a problem. All right, what about the third system?
It is linear.
Yeah, this one is linear. And he is a 2x2. He's linear because every time a variable shows up, it's raised only to the power of 1. It's never in the denominator, it's never under a radical, it's never in an exponent. What about the third system? I'm sorry, the fourth system, sorry. What about this last one?
It's non-linear.
There's a lot of stuff here that wants to flag our brain, right? Like the square root here, and the square here, and maybe the e here. All of those are kind of things we associate with nonlinearity.
Actually, it is linear, right?
Right, yeah, this one is linear. So the square root of 2, that's just a constant. The y, the variable itself, isn't under the square root. And similarly here, the 4 squared, that's just 16. This is the same as 16x. So there's nothing weird being done to the x itself. So we got to look very carefully. Remember, it's what's going on with the variables that makes the system linear or nonlinear. Those constants can be whatever they want. So this is a linear 2x2 system also. The square root of 2 is just a constant. Y is not under the root. And similarly here, the 4 squared, that's just 16, is also a constant. The x is not being squared. And E also just a constant, right? E is about 2.71 is just a constant. Nothing happening with the variables here. So this last one is a little bit deceptive, but you do want to be on the lookout. These can make good true-false questions, right? Like on your exam 4, I could give you the system and ask you to classify it as linear or nonlinear. And even though there is a square root, there is a power, there is an E, this is still a linear system because none of that stuff is being done to the variables. So it's really all about what's going on with the variables. All right, well, I've got you here in this classification scheme. Let's talk about some non-2x2 systems. Is this system linear or nonlinear? The top right system there.
Nonlinear.
Very good. This is a nonlinear system because of the x squared. What are his dimensions? So like these are all 2x2s, 2 equations, and 2 unknowns. Remember, the first number is the number of equations. The second one is the number of variables.
It's a 3x3 because there's 3 variables, x, y, and z.
It's true that there's 3 variables, x, y, and z. So the second number has to be a 3. But there's only 2 equations. So this is a nonlinear 2x3. So this first number here, this is the number of equations. And this guy is the number of variables. So here I have 2 equations. Each one has 3 variables. So that is a 2x3. All right. One or two more. What is this guy? Linear or nonlinear?
Linear.
Good. This one is linear. Every time we see a variable, it's upstairs. It's raised just to the power of 1. So this is a linear. And then what are its dimensions? So Jalen is half right there. The first number is a 3 because I've got 3 equations.
3x2.
Yeah, this one would be a 3x2 because I've got 3 equations and 2 variables, x and y. Okay. I think that's enough of this, right? Just figuring out if a system is linear or nonlinear. It's all about looking at what's going on with the variables. If any of the variables are raised to a power other than 1, if any of the variables show up under a radical, or if any of the variables showed up downstairs or in an exponent, then that would be nonlinear. Maybe just one more example here. I don't mean to be annoying, but like x minus e to the y equals 3, or 2x plus y equals 0, or 1 over x minus y equals 1. this would be a nonlinear 3x2. Three by two because three equations, two variables. Nonlinear because of the e to the y and the 1 over x. Both of those would make this nonlinear. Okay. So watch out for sneaky things like this in true-false questions. Some systems might have things in them that make us think nonlinear stuff, but are actually linear. Remember, it's all about the variables. Where are the variables? What's being done to them? It turns out that this splitting into linear and nonlinear, it's kind of like splitting all the things in the universe into apples and non-apples. It's kind of silly in one sense, because there are way more non-apple things than there are apple things. But at the same time, it's very, very important because of the following fact. Solving nonlinear systems is very hard. Like usually impossible. I don't mean like solutions don't exist. I mean, even if you have a nonlinear system where you're 100% sure that a solution exists, finding that solution exactly is almost always impossible. And I don't just mean for us as pre-calculus students, I mean in general, mathematicians are terrified of nonlinear systems. Linear systems, on the other hand, we know basically everything about linear systems. And by that I mean we can tell when they have solutions. And how many solutions. We're good at finding the solutions. When they exist. And there is a whole branch of mathematics it's called linear algebra, dedicated to these things. So nonlinear systems are bad news bears. We really don't like nonlinear systems. Linear systems, on the other hand, are really well understood. We know everything there is to know about linear systems, and through the study of linear systems, we have developed an entire branch of math called linear algebra, which has been startlingly useful. Linear algebra, I know that this is a pre-calculus class, so we're all pretty gung-ho about getting to calculus, and calculus has been one of those tools that's been massively useful all around the world in many, many different fields. Linear algebra might be more important. Linear algebra is probably the most ubiquitous single area of mathematics anywhere in the sciences, engineering, or certainly within math itself. Linear algebra has its fingers in everything, which is one of the reasons we talk about it here. It's also relevant for calculus in a handful of different ways. Okay, so we will focus on linear systems because nonlinear systems are rough. So the only thing I could ever ask you to do with a nonlinear system is tell me it's nonlinear. There are three basic methods for solving linear systems. I'll say for investigating linear systems. How about investigating / solving? Because there isn't always a solution. And not all of these methods are created equal. One of them really sucks. One of them kind of sucks, but works okay in certain cases. And one of them is awesome, works all the time. The first, your book calls the graphical method. This is where you graph all the equations. And look for the point or points where the graphs touch. Intersect or touch. Okay, that point would be the solution. The second method, one you're probably familiar with from high school, is called substitution. This is where you solve one equation for one variable, and it'll be in terms of the other variable. Then plug that expression into the other equation or equations. Finally, you solve that equation and back substitute to get the other variable. And just for fun, I will work one problem today through substitution. The graphical method sucks. It never really works. Sometimes it will give you a reasonable guess, and that's as much as you can hope for. Because, looking at a graph that we draw by hand, it's very hard to say exactly what the coordinates of the point you're looking at are. Sure, that point might be 7,5, or it might be 6.9, 5.2. It's very, very hard to tell. Substitution, this sucks less. This, for a 2x2 linear system, is fine. But it does not work well for 3x3s. And if you ever try to solve a 4x4 system through substitution, you will want to kill yourself. It'll take forever. And I guarantee you there will be a mistake somewhere. And it's just not a fun thing to do. This method that works really well for everything is called elimination. And elimination is where you perform what are called row operations. So you think of each equation in the system as a row, and you perform some operations on those rows to eliminate or get rid of one or more of the variables. So you can solve for the remaining variables, or remaining variable. Then, just like substitution, you back substitute to get the other variables. Might be 1, might be 2. Okay. Graphical method, this sucks. Even in the simplest possible cases of a 2x2 system where the solution is an integer or a point with integer coordinates, you still can't be sure. Graphical method is just terrible. It's not even really a method. Substitution, this kind of sucks. It's okay for 2x2s. Elimination, this is awesome. It always works. And it's the fastest. Slash easiest method. Also, this generalizes to higher dimensions, including infinite dimensions and matrices. So we really like elimination. And there will be problems on your exam 4 where I tell you solve the system using elimination. And if you do it using something else like substitution, I won't be able to give you credit. So kind of if there's one thing that I want you to take away from sections 10.1 and 10.2, it is an understanding of the elimination method. But I'd be doing a shitty thing as a math teacher if I didn't first demonstrate the first two methods. We're just going to do this quickly. I know everybody has seen substitution before. The graphical method, like I said, isn't really a method, but it can help us to understand what's going on a little bit by thinking about the picture. Okay. So these are your methods. Basic ideas behind how they work. Let's take a look at a system. We'll solve it graphically. Or we'll attempt to solve it graphically, and then we will actually solve it using substitution. So how's about 2x minus y equals 5 and x plus 4y equals 7. Graphically. What we need to do is graph both of those equations. Both of them are linear equations with two variables, so both of them have a graph, which is a straight line. Let me call this first one equation 1. Let me call the second one equation 2. That way I've got names for them. I can refer back to them if I need to. I think the easiest way to graph either of these would be to just go ahead and put them into that y equals mx plus b form. So I have 2x minus y equals 5. This means that negative y is equal to negative 2x plus 5. And that means that y is equal to 2x minus 5. So this is a line with slope 2 and y-intercept negative 5. Doing the same thing with equation 2. That is x plus 4y equals 7. Which means 4y is negative x plus 7, which means y is negative 1/4 x plus 7/4. So this is a line with slope negative 1/4 and y-intercept 7/4, which is 1.75 or 1 3/4. So I can sketch each of these graphs. maybe just so I can have my colors here, I'm going to do the coordinate axes in black. Here's my x-axis, here's my y-axis, and just give myself a few. Few tick marks to play with. Okay. So that first line, 2x minus 5, y equals 2x minus 5, slope 2, y-intercept negative 5. So I'll graph him in purple. Here's his y-intercept, negative 5. And the slope being 2 means if I go over 1, I'll go up 1, 2. So he also has the point 1, comma, negative 3 on him. Also has the point 2, comma, negative 1 on him. So we've got some points there. I can draw this line. Here it is. This is the graph of equation 1. The other line is y equals negative 1/4 x plus 7/4. Remember, 7/4 we said is 1 3/4 or 1.75. So that y-intercept should be right about here. And then a slope of negative 1/4 means if I go over 4, I will go down 1. So if I come over 4 units, 1, 2, 3, 4, I will have come down 1 from 1 3/4 to just 3/4, which is like right about here. So it's not perfect. I am limited in my art skills and limited in my estimation skills, but there's the graph of equation 2. And our solution is the point where these two lines touch. So this is the solution. And it looks like that solution, which again is a point, is an ordered pair. The x value is really close to 3. The y value is really close to 1. It's hard to say for sure because my picture is flawed. But if I had to guess, based on my picture, which I did as good a job drawing as I can, I would say that solution is about 3, 1, somewhere in that neighborhood. Maybe it's 2.9, 1.2, something like that. Could be pi, comma, 0.95. I don't really know, but somewhere around there. Mostly the graphical method is helpful for kind of building an intuitive understanding of what the solution to a system looks like, right? The solution to a system is the point where the graphs touch. If you take x equals 3 and y equals 1, you could plug those in here and see if you get a true statement in both equations. That's what it means to say we solve both equations simultaneously. So if I plug in 3 for x and 1 for y, is this true? Well, I get 1 plus 4, or sorry, 3 plus 4 times 1 equals 7. That's 3 plus 4 equals 7. Yeah, that is correct. And if I plug in 1 for x and 3 for y here, or sorry, 3 for x and 1 for y here, do I get a true statement? Well, it would be 2 times 3 is 6, minus 1 equals 5. Yeah, that's true. Okay, so we can verify that that works. We can check that plugging x equals 3 and y equals 1 makes both equations true. So this is the solution. But this whole draw the graph, take a guess, then check, kind of sucks, right? I mean, honestly, it sucks a lot. Because what do you do if you don't get a true statement? You know, what do you do if your guess turns out to make one of the equations false? Well, now you're back where you started. You got nothing. So the graphical method really is terrible. There's no two ways about it. This is not really a method at all. But we can solve that same system using substitution. So let's do that. First, let me just write the system down. 2x minus y equals 5. X plus 4y equals 7. So what substitution says, it says take one of these equations and solve it for one of the variables. Does not matter which equation or which variable. So I'll take the second equation here and solve it for x. This means x is equal to 7 minus 4y. Then I can plug this into the other equation. And it is important that you plug it into the other equation, not the same equation you used to get this, because if you plug this back in here, you'll just get 0 equals 0, which is true, but not helpful. So if I plug into equation 1, (2x minus y equals 5), that will become 2 times, well, x is 4 minus 7y. I'm sorry, 7 minus 4y minus y equals 5. So in place of this x, I'm going to write this expression, which I know is supposed to be equal to x. It's important that you put these parentheses here because this 2 is attached to this x, which means it's attached to this whole thing. Now I distribute the 2. I get 14 minus 8y minus y equals 5. Combining the y terms on the left, negative 8y minus y is negative 9y. And subtracting 14 from both sides, 5 minus 14 is negative 9. I get negative 9y equals negative 9. And then dividing both sides by negative 9, I get y equals 1. So this y value here, this 1, is correct. And we can find it by substitution. We still need to find x. So our last step is to back substitute y equals 1 into either equation. So if I put y equals 1 into equation 1, 2x minus y equals 5. This will become 2x minus 1 equals 5. Adding the 1, I get 2x equals 6. And then dividing by 2, I get x equals 3. Okay, so we do arrive at the solution. Therefore, the solution is the ordered pair (3, 1), right? X, y, where x is 3 and y is 1. So this is using substitution to solve a 2-by-2 system. It's not hard, and it makes a certain amount of intuitive sense. We want both of these equations to be true at once. So we solve one of the equations for one of the variables. That means if x comma y is an ordered pair that's satisfying this equation, x is automatically 7 minus 4y. If I want x and y to satisfy the other equation also, I can take this and plug it in for x here. And that's what we did. And that's how we found y. Once you get y, you can back substitute that into either original equation, because we're looking for a point that's on both lines. Plug that y value in, and you'll get x. The disadvantages of this method, though, are many. First, the particular system that we chose to work with here has a unique solution. And substitution works great on 2x2s where there's a unique solution. But there are also systems that don't have any solutions, and there are systems that have infinitely many solutions. And the substitution method isn't great at detecting that last thing. It's not great at detecting the first thing either, but it will if you're careful. The other big issue here is that while this works fine on a 2x2, if you had 3 equations and 3 variables, then when you solve one of the equations for x, say, you'll have both x's, or you'll have both y's and z's left. So then you can plug that back into the other 2 equations, and then you'll have 2 equations with 2 unknowns. That's now a 2x2. You can solve that 2x2 by substitution. And then finally, once you have x and y from that, or sorry, y and z from that, you could back sub to find x. It's just terrible. So the substitution method, even if you're very smart about it, gets hideously ugly as the size of the system grows. The elimination method, which is what I'm going to work with for the rest of class here, is nice with 2x2s, and it's nice with 3x3s and with 4x4s. It never gets ugly. It always stays nice. So I'm going to use a different system now. We solved that system twice. I don't see any point in solving it a third time. And we're going to transition to using a different method. We're going to transition to using elimination. And of course, to do that, I need to kind of describe to you what it means to eliminate. So this is where you, like I said, perform row operations to eliminate or get rid of a variable. Then solve for the remaining variable. And finally, backs up to get the other. And there could be multiple others, but here 2x2s, there's just 2 variables. What are the row operations? Well, there's 4 basic things that you can do to a system of equations. 4 operations that you can perform on the system without changing the solution. The first one, you can swap any 2 rows. So write 3x plus 2y equals 14, x minus 2y equals 2. That's the same as x minus 2. If I just wrote this equation first and this equation second, doesn't change anything. Same system. Still asking for the intersection point of those same lines. Second, you're allowed to multiply any row by a non-zero constant. Right, you know that if I give you an equation like x minus 2y equals 2, like this second equation, you can multiply on both sides of this equation by 3, and it doesn't change anything. It's still the same equation, it's just written a little differently. We do that shit all the time, right? Multiply both sides by 7 or divide both sides by 3. You can multiply through any row by a non-zero constant. And that means you can also divide through any row, right? If I want to divide by 3, that's the same as multiplying by 1/3, as long as that constant isn't 0. You can add one row to another. You can add one row to another row. So here I might leave row 1 alone, but change row 2 by adding row 1 to row 2. So you can take any one row and add to it one of the other rows. And then the last thing, and this is kind of the one that we're going to use more than anything else once we get comfortable with this, is combining items 2 and 3. You can add a multiple of one row to another row. Really, this is just taking the second thing and the third thing and combining them into a single thing. But these are the operations that you can do to a system of equations, which I guarantee you will not change the solution to that system. So if you can do these operations, but use them to rewrite the system in a way where one equation just says like x equals 5 and the other one just says like y equals 7, then immediately you can read off the solution, 5, 7. We're going to get there. We're going to build our way up gently. There is a notation for these row operations that I'm going to show you. And I want you to learn that notation here while things are simple before we get into the bigger systems, because you will need that notation when we talk about bigger systems. So, does anybody see a row operation that I could do that will help me get rid of one of these variables?
Multiply by 3, -3.
I could multiply through row 2 by -3, right? Because then I'd have a positive 3x here and a negative 3x here. And if I did that and then added the rows, the x's would go away, right? Let's try that. There's no harm in doing that.
Actually, y already would go away because it's 2 and -2, right?
Good, yeah. So we realize the y's are actually already in a good position to eliminate. So you could do either one. We could multiply through row 2 by -3, and then in a separate step, add row 1 to row 2, and that would kill the x's. Or we could, as our very first operation, just add row 1 to row 2, and that will kill the y's. Let me do that, and let me show you the notation. I'm going to think of this as being a modification to row 2. So capital R means new row. New row 2 is going to be equal to old row 2 plus old row 1. That's notation. This means the new row 2 will be equal to the old row 2 plus the old row 1. And the way I write the result, I'm just going to copy down row 1. I'm not changing row 1, I'm just changing row 2. So my row 1 stays 3x plus 2y equals 14. But my new row 2 is going to be my old row 2 plus my old row 1. So I'll have 3x plus 1x, which is 4x. I'll have -2y plus +2y, which is 0y. And I'll have 2 plus 14, which is 16. And just like that, we have eliminated y from equation 2, which now reads 4x equals 16. Right, 0y is 0. So that bottom equation just says 4x equals 16, and I can solve that by dividing both sides by 4. I get x equals 4. So we eliminated the y from equation 2 by using a single row operation. That left us with an equation that only had x's in it. Solve that equation. The very last thing we do here is back sub x equals 4 into, you can go into any equation as long as it has both x's and y's. I might go into the equation 1, right? If I go into the original equation 1, we get 3 times 4 plus 2y equals 14. 3 times 4 is 12. So this is 12 plus 2y equals 14. Subtracting 12, I get 2y equals 14 minus 12 is 2. Dividing both sides by 2, I get y equals 1. So the solution to this system is x equals 4, y equals 1. In other words, the solution is the ordered pair 4, 1. And that's it. That's elimination. Short and sweet. Very simple. This notation for row operations is probably new to you, even if you've seen elimination before. So if there's one thing that I'm introducing today that I think probably most of you haven't seen, it is a concise and direct notation for these row operations. There are other ways of writing this stuff, and I know that some other teachers like to, just say when you add these equations, you just put like a little line down here and you write the resulting equation underneath. That's a shitty notation. When we talk about bigger and bigger systems, and you'll see some of these problems in your homework, we want to preserve the physical structure, the geometric structure of the system as we perform these row operations, because oftentimes it's going to take more than one. Are there any questions about what we did here? Any of the notation or why we did any of it or anything at all? Okay, then. Before we proceed, I need to tell you something. One of the nice things about linear systems, this is a theorem, that all linear systems regardless of their size fall into one of the following categories. there's either a unique solution right? One point that lives on both lines or lives on all of the graphs, satisfies all the equations at the single time. It's also quite possible that there is no solution. And kind of the hardest case to handle is infinitely many solutions. And there, in the 2x2 case, there's a picture that corresponds to each of these. So the unique solution picture is where you've got two lines with different slopes and they meet at a single point. Right, like everything we've seen so far falls into this category. Right, and your solution is right here. That is your unique solution. We also know that if I give you two lines and they have the same slope, but different y-intercepts, those lines are parallel. Then there is no solution. There's not going to be any point that lives on both lines because two parallel lines, they never touch. Unless they're secretly the same line. So if the two lines have the same slope and the same y-intercept, maybe something like this. And also like this. Well, then those are the same line. So any point on that line is a solution. And I want to draw your attention to a fact here. This does not mean that every point in the plane is a solution. For example, this point over here would not be a solution. But every point on the line are solutions. So in the unique solution case, if you run the elimination process, you will get that unique solution. In the no solution case, if you run that elimination process, you're going to arrive at something called a contradiction. And that will tell you that there is no solution. And then you just stop. You're done. There's no solution. In the infinitely many solutions case, you will run your elimination process and you're going to end up with something called a tautology. Has anybody heard that word before? Any logic people in the room? A tautology is a proposition which is true regardless of the value of any variables. It's a statement which is always true. It's like the opposite of a contradiction. So if you run elimination and you get a contradiction, no solution, you stop. If you run elimination and you get a tautology, that means there's infinitely many solutions. But then you need to find some way to tell me which points are not solutions and which points are solutions. And I'll show you how to do that. Okay. Let's see, is there one we haven't done? Did that one? Yeah, let's do one more nice example of an elimination problem. Let's solve 3x minus y equals 0 and 5x plus 2y equals 22 by elimination. Oh, sorry, the lighting conditions here keep changing. Is this blind? Oh. So generally the way this goes, you're going to pick a variable to try and eliminate. I can try to eliminate the x's, or I can try to eliminate the y's. 3x and 5x, I would have to modify both of these to get negative coefficients here, right? Like if I multiply this first row by 5 and I multiply the second row by -3, then I would have positive 15x and negative 15x here. I think it's easier to eliminate the y's because I've got a -1y here and a positive 2y here. So all I have to do is multiply through equation 1 by the number 2, and I'll have the y's ready to eliminate. So my first row operation here would be to make my new row 1 equal to 2 times my old row 1. And my advice to you when performing row operations is first copy down the row that doesn't change. So the second row isn't changing here. He stays 5x plus 2y equals 22. Then write in the stuff that does change. So row 1, I'm multiplying everything by 2. So that's going to become 6x minus 2y equals 0 times 2 is still 0. Now I'm going to add the rows. And I'll think of that like I'm going to take row 1 and add it to row 2. So my new row 2 will be my old row 2 plus my old row 1. That's the notation. So this time it's row 1 that isn't changing. I have 6x minus 2y equals 0 still there. And then if I add this to this, this will become 6x plus 5x is 11x. 2y plus -2y is 0y. And 22 plus 0 is 22. And now that second equation no longer has any y's. We have eliminated y from equation 2, which now reads 11x equals 22. And if I divide both sides there by 11, I get x equals 2. Back subbing x equals 2, and I can go into any equation I want as long as it has both x's and y's. I'll go into the original equation 1. That will give me 3 times 2 minus y equals 0, which means negative y equals negative 6, which means y is 6. So that's it. Thus, our solution is the point 2, 6. So this system had a unique solution, one point where those lines cross. And that point is 2, 6. Any questions on the elimination steps here? And you see how clean this is, right? It's really, really fast. If I didn't write all these words, it would be even faster. All right, I'm going to do 2 more examples, which means we're going to go a little bit over the time limit here, and I apologize for that, but I think it's important that we get through this. It's nice to have it all in one package, especially with the holiday on Thursday. Really quick, your homework has both 10.1 and 10.2 stuff in it. I'm going to record a video lecture for 10.2 that you will need to watch sometime between now and next Tuesday. I strongly suggest watching it as soon as it comes out. And that will talk about solving 3x3s. And it will also introduce the notation of matrices. So here, let's solve the system 8x minus 2y equals 5 and negative 12x plus 3y equals 7. And again, we're going to use elimination. This time, neither variable is an easy target. 12 is not a multiple of 8, nor is 3 a multiple of 2. But I can, with a single row operation, set things up nicely. If I multiply through row 1 by 3, then I'm kind of getting closer to this. And if I multiply through row 2 by 2, then I'm kind of getting closer to this. So my new row 1 will be 3 times my old row 1. And I'm also going to multiply through row 2 by 2. So I'm going to do 2 of these row ups at once. 3 times row 1, that's 8 times 3 is 24x, minus 2 times 3 is 6y, equals 15 times, 5 times 3, which is 15. And in the same step, I'm going to multiply through row 2 by 2. Negative 12 times 2 is negative 24. So negative 24x. 3 times 2 is 6, so I'll have plus 6y equals 7 times 2 is 14. And something interesting happened here. I thought of this like I was going after the x's. I know if I multiplied this by 3 and this by 2, I'll get positive 24 and negative 24. But at the same time, I set up the y's to be eliminated as well. And that's an indication that something funny is going on. So now, as before, I'll add the rows. I'll say my new row 2 is old row 2 plus old row 1 staying the same, 24x minus 6y equals 15. 24 plus negative 24 is 0x. Negative 6 plus positive 6 is 0y. And 15 plus 14 is 29. And now equation 2 is a problem. because equation 2 now says 0x plus 0y equals 29, i.e. 0 equals 29, but 0 is not equal to 29. This is a contradiction. So if you assume a solution exists, you arrive at a contradiction, which means no solution exists. And that's it, you're done. This system has no solution. These lines are parallel, but they have different y-intercepts. If you put both of these into the y equals mx plus b form, you'll see that they're both lines with slope 4, but one has y-intercept -5/2, and the other one has y-intercept +7/3. These are parallel but distinct lines. The last thing I need to show you is how to handle a system with infinitely many solutions. And then I will let you go. These start off kind of similar to the no solution systems. But like I said, when we introduced the concept, once we know that there are infinitely many solutions, we're not done. Because we still need to characterize them or describe them. So if I think of this like I'm going to try to eliminate the x's, I would multiply row 1 by 4 and row 2 by -3. That'll make those x coefficients into 12 and -12 respectively. So my new row 1 will be 4 times my old row 1. And my new row 2 will be -3 times my old row 2. Row 1 will then be 12x minus 24y equals 48. And my row 2 will be -3 times 4 is -12x. -3 times -8 is +24y. And -3 times 16 is -48. And continuing in the same fashion as the other problems, if I now add the rows, row 2 is old row 2 plus old row 1. My first row is still 12x minus 24y equals 48. But row 2 is going to become 0x plus 0y equals 0. And that second equation (0x plus 0y equals 0) says just 0 equals 0, right? 0x is 0, no matter what x is. 0y is 0, no matter what y is. So this equation just says 0 equals 0. And this is called a tautology. You ever take a class in formal logic? Tautologies and contradictions are the opposite of each other. A contradiction is a statement which is never true, regardless of the value of the variables. A tautology is a statement which is always true, regardless of the value of the variables. 0 equals 0 is a tautology. what that tells us is that there are infinitely many solutions. But like I said earlier, this doesn't mean that any ordered pair XY is a solution. For example, 0, 0 doesn't work. Try it. Look at this original system. If you plug in 0 for X and 0 for Y, then you get 0 equals 12. You plug in 0 for X and 0 for Y here, you get 0 equals 16. Neither of those are true. So I know there are infinitely many solutions, but how do I describe them? Well, let's go back to this picture really quickly. Right? We said infinitely many solutions. Okay, that means that those two equations are really the same line. And that points that aren't on that line wouldn't be a solution, right? 0, 0 is a point that's not on the line we're talking about in the problem above. But what about the points that are on the line? How do I describe those? Well, it's not too hard. Here's the standard way of doing things. What this does mean is that given any value for X, say X equals T, we can find a corresponding value for Y such that the ordered pair XY is a solution. Those words are great, but what does that mean? Well, it means you're going to let X be a free variable. Sometimes you'll leave X as X. Sometimes you'll write X equals T. It's the same thing. And some of the problems in your homework ask you to just leave X as X. Some of them say write the solution in terms of a parameter T. In either case, what you're going to do is you're going to solve one of your equations for Y. So let me take (3x minus 6y equals 12). If I plug in t for x, I know I should be able to find a corresponding y value. So 3t minus 6y equals 12. Let's subtract the 3t over. I get negative 6y equals 12 minus 3t. And then I divide both sides by negative 6. And that will get me y equals 12 divided by negative 6 is negative 2. Negative 3t divided by negative 6 is plus 1/2 t. So your solutions here are any ordered pair of the form t, comma, -2 plus 1/2 t. That's it. So if you have infinitely many solutions, that means you need to describe them. What are they? Well, they're all the ordered pairs that live on that line. Remember, both of those equations are the same line. And the way you describe those is by just letting x be a free variable and figuring out what the y value has to be. And you could have done this with either of the original equations. All right, I chose to use the 3x minus 6y equals 12. But you could have used the 4x minus 8y equals 16 because they're the same equation, just written differently. And in any case, you will end up here. Here. All right. So this has been your quick and dirty introduction to linear systems, the 3 types of linear systems we encounter, those with unique solutions, those with no solutions, and those with infinitely many, and the 3 standard methods for solving them, just looking at the graph and crossing your fingers, the substitution method, and the elimination method. I think I've badgered you enough that you understand that the elimination method is the one that we care about. It is the one that works well in all 3 cases. It is the one that generalizes to higher dimensional systems, including infinite dimensional systems. Whereas the substitution method, you can try to use it in a 3x3 or a 4x4, but you're going to hate yourself. The graphical method is literally impossible outside the 2x2 setup. So it's really all we have. Elimination is all we have until we learn about matrices. And matrices come from thinking about elimination. We don't have class this Thursday because it is the Thanksgiving holiday, but there will be a lecture posted. I will record a lecture for you, and that lecture will be posted to the announcements, the same place you found the lecture before exam 3. That lecture will talk about 10.2, which is systems with larger size, 3x3s, 4x4s. We will use elimination for all of those. I'll talk a little bit about the geometry of those higher dimensional systems. And then I'll show you how to use matrices to solve those higher dimensional systems. This same elimination process can be applied to matrices. Matrices sound scary. They look a little scary, but I promise you they're not scary. It's the same shit. We just don't write the variables. We just write the numbers instead. You let their location on the page tell you what variable they are attached to. Aside from that, it's the same thing. The other thing that you'll learn in that lecture is a kind of consistent pattern, a way that you can always apply the elimination procedure to get the right answer. So you don't have to like guess and end up chasing your own tail. But that's it. That's where we're going. And that's it from me. I'm sad to say I won't see you guys for a full week, but I won't. I'll see you all next Tuesday. Please, everybody, have a safe and healthy holiday. If you have any questions for me, you know how to get a hold of me. Canvas, Discord, email, all work. Of course, I have my office hours Monday, Wednesday, and Friday from 1 to 2. I do have an office hour this Wednesday. I will not have an office hour this Friday because I will be out of town. But that's it from me. Take care, guys. Work hard. If there's anything I can do to help, please let me know. Bye.